So I want to do just a couple little example problems here on exponential growth and what this equation really means, how we can use it. So we have here the differential form as well as the integrated form and a little plot of x versus time, which is basically this second equation here. So how we would do a problem like this is, let's say we have at some initial time here, which we'll call t0, we can say we have some initial population x0, and we want to know after t equals 5 days, so here we have t0 plus 5, what is the population in the reactor? What is this x sub t? So let's say our x sub 0 is 25, and we're going to say milligrams per liter. So maybe this is some bacteria that we measure by actually weighing it. And so x sub 0 is 25 milligrams per liter. Mu max, we'll say, is 0.20 per day. And KD is equal to 0.05 per day. So I can just plug KD and mu max into here. My T is just going to be 5 days. And when I plug all these things in, I get that after 5 days, my x sub t is 52.9 milligrams per liter. Or if I had rearranged this equation up here, I can rewrite this as x sub t over x sub 0 equals e to the mu max minus k sub dt. And so x sub t over x sub 0 is 52.9 over 25, which in this case is 2.11. And that's just equal to e to this mu max minus kd is 0.15 times 5 days. And so what this means is, for any 5-day period, the population is going to a little bit more than double. When we go from t sub 0 to t sub 0 plus 5, the population multiplies by 2.11. So it goes from 25 to 52.9. If then we redid this starting at 52.9, if that was now our new population at time 0, and we wanted to know 5 days after that, so t sub 0 plus 10, what is the population? Well, it's 2.11 equals e to the 0.155, so 2.11 times 52.9, and we get 111.9 milligrams per liter is what you're going to get after 10 days. Okay? So in an engineered system, frequently this is what we have in our biological reactor, and we need to, what we really want is our population of organisms to be balanced with how much food is coming in. And so as they grow, we need to remove some to make sure the population doesn't get to a level where it can't be sustained by the food that's coming in. And so if we think of this in terms of like a reactor with some food coming in, and our population is in this reactor growing, we have to periodically remove some of the population to keep it constant. And so you can think of this as the population sort of grows from some initial time to some future time, and then we remove some of those organisms and we go back to here, and it goes back up over and over and over. Now, really, this is in a flow-through system, usually, so we're kind of continuously removing organisms as they're growing. So in this case, let's say we have our initial population is 1,000 milligrams per liter, and we we are asking how much milligrams per liter must be removed per day to keep the population constant. So in other words, we're at 1,000, we're going to grow. How much are we going to grow, and therefore how much do we need to remove? So using the same parameters, we can say, well, our x of t is equal to x sub 0, 1,000, e to the 0.2 minus 0.05, and then t is just 1 day. And we get, I think, let me make sure I did this right. Yeah, so x sub t is equal to 1,161 milligrams per liter. We went from 1,000 to, after 1 day, 1,161. So if we want to keep this constant, we need to remove 161 milligrams per liter to keep at 1,000 per day, right? So you should just kind of become familiar with this equation, what the parameters mean, how what this graph looks like, what's t0, what's x0, what's x sub t, and thinking about how we would actually use this in an engineered system to keep a population constant. And that's all I wanted to talk about with that equation and population growth.